Everybody have your paper out? Alright, today we're going to talk about intermolecular forces and intramolecular forces. Because I'm going to read that in a minute. Okay. So intermolecular and intramolecular forces. Yes.
Oh, I thought you were asking.
Well, I didn't ask the question yet.
I mean,
Okay, so the first thing I want us to look at are the prefixes. Okay, so we have inter and intra. So what does inter mean? Between. Okay, so intermolecular forces are going to look at forces between. Intra means what? Within. So that would be looking within. Okay, so let's look at some examples. An interstate. Where does an interstate go? Like a lot of you might be taking I-71 in the next couple days. Never heard of it? Okay, so I-71 runs from where to where? Anybody know? What? Pennsylvania to? No, wrong direction. Go south. We're heading more like towards like the Florida area. How about Interstate 75? Where does that one run from? What's what? About Michigan to Florida. Okay? So it goes, it's linking from one state to the next. Okay? So when we look at intermolecular forces, those are forces between molecules. Okay, so that's linking one water molecule to another. Intramolecular forces would be like, you heard of intramural sports.
yeah.
What's an intramural sport? Right, so it's within your school. Okay, so they're really big in college. You have your intramurals, everybody gets together, get your friends, and you play sports within your school. What is an intercollegiate sport? Intercollegiate. Yeah, so it's between other schools. Okay? So, inter is going to be between two molecules. Intra is going to be within a molecule. So what's holding the hydrogen and oxygen within the water molecule together? Yeah, we're taping this right now.
What's up?
Inside permission slip on the tape.
Okay. So, inter is going to be between molecules. Intra will be within a molecule. Okay? We good on those prefixes?
Yes.
All right. So, let's start with intra, because you've talked about all these before, except for one. Okay, so intramolecular forces. So we said an intramolecular force is a force within a molecule. Okay, so our first type is ionic. You've talked about ionic before. What's an ionic bond found between? A metal and a non-metal. Okay, so an ionic bond is found between a metal and a non-metal. Okay, you remember talking about Benjamin Franklin?
Oh, yeah.
Yeah, what did Benjamin Franklin find?
Opposites attract.
Opposites attract. So,
Likes repel.
metal and non-metal. So we bring a positive and a negative together.
They attract.
Do you remember what that force was called? Starts with an E. Close.
Electronegativity.
Not electronegativity. It's an electrostatic attraction.
Same thing with electronegativity.
nonmetal, positive and negative, it's an electrostatic attraction. Okay, so let's look at an example. We're going to be taking all these different types of bonds, and it's going to be leading us into talking about boiling points, melting points, vaporization, evaporation, all these different things. Okay? So we have salt. What is your table salt at home? NaCl, sodium chloride. Okay, when it is sitting at home on the kitchen table, what state of matter is it?
Solid.
It's solid. Okay, we see it in a solid state. Do you guys remember the term crystalline lattice? It is that thing. So, here is our crystalline lattice. Okay, so is this NaCl? Is that now? Not water, like someone said earlier. This is NaCl. Okay, so sodium chloride. Okay, one to one. So remember we talked about what happens if you were to break this crystalline lattice. It'd break into what?
More cubes.
Right, it would stay in this cube shape, but we would just have a smaller chunk of it. Do you remember that?
Yeah.
Okay, so we have our crystalline lattice. So, NaCl is a crystalline lattice. So, if we look at sodium chloride, what is it in its ion forms?
Na plus,
Yes.
Cl negative.
Na plus and Cl minus. Okay. So I'm going to tell you that this has a melting point of 800 degrees Celsius. Okay? So you remember we talked about single bonds, double bonds, and triple bonds? Which ones were the strongest? Triple bonds. Triple bonds were the strongest. Were they the closest together or the farthest apart? Right, they were close together, so it makes them really hard to break. Okay? So if you decrease the distance between bonds, you're going to increase the strength of the bond. So if you decrease the distance, so if we have a triple bond, that's going to increase the strength of the bond over a single bond. Yes, because the triple bond is shorter, single bond's farther apart. Okay? Now I want us to look at magnesium oxide. What are the charges on magnesium oxide? Yes. 2 plus, 2 minus. Okay? So what's going to happen is if you increase the charge, you're going to increase the strength. So what's going to have a stronger bond? Sodium chloride or magnesium oxide? Magnesium oxide. Its melting point is 2,800 degrees Celsius. Big difference. Okay, so if you increased it again, so we had a 3 charge, what's going to happen to your strength of your bond? It's going to increase or decrease? Increase. It's going to become even stronger. Good. Okay? Questions on this? All right. Let's look at the second type. Covalent, which we have again talked about before. Okay? Ionic were our strongest bonds. Covalent are the weakest. So what are covalent bonds found between? nonmetals, yes. Okay, a nonmetal and a nonmetal. All right, so we said this one was electrostatic attraction holding them together. What holds together a covalent bond? Shared valence electrons. So we have overlapping orbitals, and they're sharing their electrons. Remember we said that's really weak, it's really easy to break them apart? Okay? So we have overlapping of orbitals. Ionic, we see generally in a solid phase. We talked about solid. It was solid. Whereas covalent, we will see in all phases. Okay, we tend to see them in all different phases of matter. Okay, questions on that? No? Good? Review? Okay, the last one is something new. And that's a metallic bond. Okay, metallic bonds are the third ones. We generally see these as a solid. Okay, and what do you think they're going to be between? Metals. Yep.
So this is only for intramolecular forces?
Yes, these are all three of the types of intramolecular forces. Okay? So they're going to be bonds between metals. It was mentioned briefly. Okay? So, we have what's called the sea of electrons. So, the metals all want to give up their electrons. Okay? So they don't really belong to any one atom. So they're just flowing through together. So there's all these electrons and they're just flowing throughout each other. No one is, using an electron. They're not sharing them equally. They're all just flowing all throughout, which is why it's called a sea of electrons. It makes this a very strong bond. Okay, so this is a strong bond. Okay, ionic is the strongest, covalent is the weakest, but this one is also very strong. It's a little bit weaker than ionic. Okay, this is going to cause a high melting point. Think about metals. You usually see them in what form? A solid. And it takes extreme high heat to break them apart and melt them down, does it not? So these forces are what cause that. Any questions on the intramolecular forces? Okay, all these forces are extremely strong. They're what hold a molecule together. All right. So let's talk about intermolecular forces. Okay, intermolecular forces. These are also known as van der Waals forces. So let's start out by looking at water molecule. All right. So do you remember talking about dipole moment? Yes? So if I tell you that oxygen has an electronegativity of 3 and hydrogen has an electronegativity of 2.1, which way is the dipole moment going? If oxygen has a dipole moment of 3,
It's going to the oxygen.
or electronegativity, and hydrogen has electronegativity of 2.1, which way is the dipole moment going to go?
Oxygen.
Yes. Our resultant vector is going to go towards oxygen. Okay? So, who remembers this little symbol? Do you Remember that? We were talking about which end is positive and which end is negative? Kind of? No. Okay. So we have to figure out which end of our molecule is going to be positive and which end is going to be negative. Okay? So we just said that our force is going towards oxygen. Is that going to be a positive end or a negative? Negative. Yes. This is our negative end. Hydrogen then is going to be which end? Positive. Okay?
Could you tell that based on our ions? Since H plus and O2 negative?
No. Yes. You could do it that way.
That's like the same thing.
Yeah, you could do it that way.
In this case.
But we're doing this based off of our resultant vector. Okay? So, if I bring in another water molecule, this is negative, positive, positive. Okay,
So is there really a vector going for the 2.1 and 3? I would just say, well, 3 is stronger, so that's what the vector is.
yes.
Is that how you get
It's
that?
the difference. This vector would be 0.9 towards oxygen. So the pole would be towards oxygen. Okay? So, we have another water molecule that comes in. Okay? What kind of bond was this between the hydrogen and oxygen? Was that an intermolecular force or an intramolecular force? Intra. This is the bond holding this water molecule together. It's holding this together. It's the bond that's holding these hydrogens to this oxygen. So that's intramolecular, within the molecule. Okay? What kind of bond is this? 3 minus 2.1 gives us 0.9,
Polar covalent.
which is polar covalent. Okay, so that's a polar covalent bond. Okay, the bond that is going to hold these two water molecules together is going to be intermolecular. It is, it's the Q. Okay, so this right here is going to be an intermolecular bond. Okay? We good? Okay, let's talk about between this water molecule and this water molecule. So right in here. And we're going to talk about what kind of bond that is in a couple minutes. Between two molecules.
I was thinking molecule is like columns.
Nope. Okay, so let's talk about the 3 types. The first type we have are called dispersion forces. Depending on what book you have, later you might also see the word London with these. Some call them London dispersion forces. Your book is, right? So it just depends. Okay? So dispersion forces. These are nonpolar and generally are seen as gas. Okay? This type of force is also the weakest. Of the intermolecular forces. Okay, so we're going to say we're going to call this fluorine. Okay? So what's going to happen is you see how this electron's over on this side right now? So that leaves the positive side open. Everybody see that? So the electron's over here, so that side's more negative. So this positive is going to want to pull over to that electron. Does that make sense? Okay, so this is going to cause what we call a temporary dipole. It's a temporary attraction. Okay, this electron is circling around, right? But it's circling, we know that. We know that it's circling around through its orbit. Okay, so it's going to come around, and when it gets over to this side, these two are going to want to push apart. Does that make sense? Because now we're going to have two negatives on one side. And Ben Franklin told us that what? Opposites attract and likes repel. Okay? So, this is going to cause what's called the temporary dipole. So it's going to be together, but then every time that electron circles back around, it's going to want to pull apart. So it's not always together. Okay? So now let's look at this one. Okay? We're going to call this one bromine. So what's the difference between this one and the one before it? It's gotten bigger. Okay? So the bromine's bigger. So that means it's going to take more time for that electron to circle. Okay? So it's going to be pushing apart less often. Does that make sense? So it's going to take longer to circle. They're still going to be pushing apart, but it's not going to be as often.
So can they like get as far apart then in a circle?
Say that again. What?
Could it not get as far apart than it's there? I don't know.
Well, it'll stay apart a little bit longer.
It will.
Yeah, because it's going to take even more time for this electron to move just that little space here. So they're going to be together more also. It's going to spend more time together, but they're also going to be apart a little longer. Okay, so then this is iodine. So what's different again? What's different this time? Larger again. Okay, so again, it's going to take the electron even more time to circle. Okay, now I want you to take these three. I want you to look at the periodic table, and we're going to look at what states they're in. Fluorine is in what state? What? Yes. Fluorine is a gas. Bromine. Liquid. And iodine? Solid. Okay, so these intermolecular forces directly relate to the phase of matter. They're not together as often, they're gas. You always see, the gases are moving around really quickly, okay? Because they're only going to be together for a short amount of time. Liquids, it's taking a lot longer for that electron to come around, so they're going to stay together more. So you get the liquid state. And solids, this electron is going to take a very long time to circle, so it's going to spend the majority of its time together, so that'll give us a solid state. Everybody see that? Okay, so are we good on dispersion forces? Good. All right, second type are called dipole-dipole. Okay? So these are found in polar covalent molecules. And usually in a liquid state. Okay? Okay, so we said that this is a temporary dipole. They're only temporarily together. This one is permanent. It's a permanent dipole. So again, just like we talked about before, the positive end of one is going to be attracted to the negative end of another. So positive to negative again. Okay, so the strength of these dipole forces increases as there's a difference in distance between them. Okay, so there's an increase in distance, gives us an increase in dipole. Okay, so if I gave you ICl and SO2, which one is going to have a higher dipole force? ICl or SO2? ICl. They're farther away from each other, so there's going to be a higher force. Yes?
What do you mean by dipole? Increase in dipole?
It's an increase in the force. The dipole is the force, the attraction of them. There's going to be a stronger pull.
So the further they get away, there's a stronger pull.
Yeah, because they're going to pull, they're going to want to pull more to get together. Because they're going to have a higher differences in negativity, so they're going to want to be together more. Does that make sense?
Since they want to be together, whether it's from the
Yes. Okay. Alright. So we have one more type. And that's hydrogen bonding. Okay? So I'm going to erase this. Okay? And we have 3 hydrogen bonding. Okay? These are in polar covalent molecules. And this is a very specific dipole. Okay? It's specific. You'll see a lot of places where they call it a dipole-dipole, but I want you to know it's a specific dipole reaction. It's not the same as this dipole. This reaction only happens between hydrogen and either nitrogen, oxygen, or fluorine. So there's going to be an attraction between hydrogen and nitrogen, hydrogen and oxygen, or hydrogen and fluorine. Okay? So let's look at an example. We have hydrogen to fluorine, hydrogen to fluorine. Hydrogen has an electronegativity of 2.1. Fluorine has an electronegativity of 4.0. So, which way is our vector going to be going? Towards fluorine. Okay? So towards fluorine. So, which end is our positive end?
Your hydrogen.
Yes. And our negative end? Fluorine. Oh, that one was bad. Okay. So this hydrogen is going to be attracted to that fluorine. Okay? So this bond right here is a hydrogen bond. And this only happens between hydrogen and fluorine, hydrogen and nitrogen, hydrogen and oxygen. Okay? So this bond is intra or intermolecular? Intermolecular. It's between 2 molecules. This bond is inter or intra. Intramolecular. It's a bond within the molecule. Are we seeing the difference between them? Okay. So, this bond right here is the strongest of all of the intermolecular forces. Okay, so that is our strongest bond. Questions on that? Okay. Now I need a volunteer.
I'll do it.
All right.
Brave soul.
Do I need to come off?
Yeah, I need you to come up. We're not making anything explode. No. Okay. So I need you to put 50 milliliters of distilled water into this beaker, or graduated cylinder, and 50 milliliters of ethyl alcohol into this graduated cylinder. So do that first.
Okay.
Don't mess up.
Should we get goggles for this one?
I'm
Should we
scared.
gloves?
You're okay.
I don't know if I believe you, to be honest.
It's actually hydrochloric acid.
It's probably is.
It's really water.
You're shaking.
I don't know.
Yeah, if you pour it slower, faster. Slower.
Is it 50?
50.
Oh, well, it only has to be.
That's okay. Ethyl alcohol. Did you get that from Horn? Good. Okay. So the next thing I want you to do is pour both amounts, the water and the alcohol into this graduated cylinder. Yeah, just wash it. It's like acetone.
So we put this in here.
Both of them are going to go in there. So we're adding 50 milliliters and 50 milliliters, which would be our total volume. 100 milliliters. Go.
Okay, it doesn't matter which one.
No, it doesn't matter which one's first.
There's one, right? 50 moles. Oh, you're terrible.
I'm so serious.
Remember, you're on camera, so don't mess up.
Oh, yeah, I am.
Okay, give it a second.
Yeah.
You did have more than 50 in that one, didn't you?
It's only like 51,
Is the alcohol going to the top?
Just more.
They are not. It's combining.
Maybe.
Wow,
that's really cool.
One more over a little bit.
Let's do it again.
So what's happening?
Well, she had a little more than 50 in them, so they're over.
Oh,
She had about 50. Okay, so she had 51 milliliters of each. What's our final volume? So she took 51 and 51, which would be what? 102, and we have 100 milliliters. Okay? Thank you. Yeah, go ahead.
What was supposed to happen?
It happened what was supposed to happen. We had 51 and 51, and we ended up with 100. Okay? So I'm going to draw what happened. Not anymore. All right. So she just took water. And ethyl alcohol. These are our two compounds. Okay? So we said that this is our what? Positive or negative? Oxygen. Negative. And hydrogen? Positive. Okay? These hydrogens are what? Positive. And this O will be negative. Alright, so this hydrogen wants to bond with that oxygen. And this oxygen wants to bond with that hydrogen. What kind of bond is that?
Double bond. It's a polar covalent.
What type did we just go over? It's a hydrogen bond.
Hydrogen.
Hydrogen to oxygen.
Hydrogen bond.
Okay? So, this is a hydrogen bond. What kind is this one? Also a hydrogen bond. Okay? These are two hydrogen bonds. So what it did is these bonds are extremely strong. So when they came together, it pulled that molecule up and made it more compact. Okay? So that's why we lost volume. Okay? It made them more compact, so it pulled them in closer together. So we lost volume.
More dense.
Mass is the same, right? Did we lose any of our two liquids? No. We just lost volume because they pulled in even closer.
Oh, so it's less. Is that what we were supposed to say? So basically, it just made a denser substance.
Exactly.
But two things.
Yep. Okay? Well, she had 51 of each. And it's at 100. So we lost 2 milliliters. Pretty cool, isn't it? Science does cool. Alright? So I just want you to remember that the hydrogen bonding is extremely strong. Okay? It's the strongest of all of the intermolecular forces.
It's the Arnold Schwarzenegger guy.
Yes, it is the Arnold Schwarzenegger of intermolecular forces. Okay? And I also want you to remember that it is a specialized type of dipole. Okay? It's only between hydrogen and nitrogen, hydrogen and oxygen, or hydrogen and fluorine. Okay? Any questions on these? No?